My title is Terahertz spectroscopy water. So I want to explain basics of their spectroscopy, and many people following me will explain many details. So this one is collaborators. So many PhD students and assistant professors, postdocs are contributing to our work, especially Peter Jepson and Shiraga and Ogawa. Contributing even today. And this is today's content. And first, I'd like to explain what is Terahertz spectroscopy, and then explain about the attenuated total reflection spectroscopy. So in the morning, we have a far ultraviolet ATR, but I will explain far infrared ATR. And explain about the water spectroscopy in Terahertz region, and application to the hydration effect I will explain. Then summarize. So this is the chart of the dielectric constant against wavelengths. So you can see in the microwave region, we have a Debye type relaxation process. So in the case of solid state material, we have spin relaxation process, of course, existed. And in the visible region, we have electronic transition. In the morning, we saw ultraviolet absorption of the water. And the infrared region, of course, we have a weight stretching and libration modes. This also describes hydration effect and also details about the cluster mode of the water. And so between these two infrared and radio wave region, we have Terahertz region. So in this region, we have some macroscopic mode of the water existing, and also, a large molecule has large mass. So if you consider intermolecular vibration mode, eigen mode existing in the Terahertz region because it's heavy. So we can monitor the large amplitude oscillation of large molecules in Terahertz region. And if you look at the water, so this is, I took this figure from the Jackson. And so we have Debye mode, this is the log scale. So we have Debye mode here, and we have visible transparent region here. And of course, we have many stretching or vibration mode here. And if you look at the Terahertz region, we have some deviation from the Debye mode, and also some broad absorption existing around 5 to 10 Terahertz regions. So I will explain later this region. And of course, many people are already studying this spectrum region using Raman scattering. This data is taken from the Dr. Ambo paper, and around 5 terahertz or 150 wave numbers, we have stretching type, collected mode existing like this. So this is called like A1G type symmetric collective motion, stretching motion. And this is very strong Raman scattering. And if you want to monitor the collective mode in water, maybe this one is a very typical or a good vibration mode. And also, if we look at the infrared active mode, that one previous one is Raman active. So symmetric mode we can see. But using infrared technique, we can see asymmetric type motion, like water dynamics, the rotating, librating. And also, if you look at biomolecules, of course, we have a hydrated water, and we can see the difference between hydrated water and also free water in Terahertz region. And as I said, large amplitude or low frequency vibration mode also existing, and there are so many water molecules existing, of course. So there are, if you look at the Terahertz region, these kinds of large amplitude motion also existing. And if you want to have an application, some medical application like cancer imaging is now many discussions existing here. And if we look at the technology of the light sources in Terahertz region, so there is a technological gap existing before 2000. So these are semiconductor-based light sources, and are always going to the 1 terahertz, decrease in the power. And if you see some semiconductor-based light sources also decreases. So there is some technological power gap existing. And also, we have, yes, of course, we have several light sources, but so light wavelength is limited. Only the gas-like narrowband line oscillation exists. But after inventing the femtosecond laser system, so very broadband light sources we obtain, and very nice, precise spectroscopic method I invented after 2000. So this is based on rectification process from using a femtosecond laser. So if you consider second order nonlinear process, normally we know there's some frequency generation or second hand. So this one is if we consider two colors, omega 1 and omega 2, so some frequency generation is a summed process. But in the same order, we have difference frequency mixing process, like omega 1 minus omega 2. And if you take these two frequencies as the same, so this is called rectification. So frequency going to 0. But femtosecond laser, you can imagine this one is not the CW, not fixed frequency, and they have many color existing. So many frequencies they included. So in such a case, we have we can take these subtractive wave generation and a very broadband light source we can get using this rectification process. So just shine this femtosecond laser light to the second order nonlinear material. We have terahertz light. How to see this? So this one is a very typical time profile of the terahertz wave using femtosecond laser light source. So you can see this is just one cycle electric field oscillation. And this period is in the order of 1 picosecond. This means that it's 1 terahertz almost. But this one cycle means that it's a quite broadband. Only one cycle. So if you take a Fourier transformation, so we can get this spectrum of light source. And now we can see this light source has very broadband from 0.2 to 3 terahertz. And the important thing is that this light source always phase of wave is fixed. Always we have this fixed phase. So this means that we can precisely determine the phase of the wave like this. This one blue is a phase spectrum. So we can precisely determine the amplitude of electric field and phase. So using these characteristics, we can determine the optical constant, not using Kramers-Kronig relationship, and just measure the transmitted light or reflected light, and measure the field amplitude and the phase. We can obtain optical constant. So this is a very important aspect of current terahertz spectroscopy. And the measurement system is very simple. This one is a light source, and this is a terahertz detector. And using femtosecond laser, we obtain the pulsed terahertz wave. And in this case, it's a transmission geometry. And we can monitor the waveform just using the gating method, using also a femtosecond light source. So using this very simple transmission geometry, we can obtain this transmitted wave, and we can see how the material absorbs the trace wave and also how large the reflection is. All right, so maybe it's just a picture of emitting from the tyrosine crystal. It's a tiny crystal. If you purchase the tyrosine, so it's a many tiny crystal you have. So if you measure spectrum, normally you make a pellet. But using our method, you don't need to make a pellet. Just put our APR prism, this crystal, and see what's happening. So this is a tiny crystal, and we just shine the trace wave pulse. And material respond like this. So you can see some waves appearing from this crystal. Now we shine the trace pulse from down. Now. And this tyrosine tiny crystal emits the sunlight. So by measuring this emitted light, we can determine the optical response very precisely. What is this? So this is a kind of impulsive response of ring or bell. In Japan, it's kane. And if you imagine the shot of the kane or ring, so we can see the eigenfrequency of this object. So Terahertz technique is similar. Just hit the material, and the material speak their eigenfrequency by themselves. So actually, we measure this ringing pattern, so in time domain, and make a Fourier transformation, we have some spectrum. This is really matched to the optical mode of tyrosine crystal. It's a tyrosine molecule to molecule vibration mode, and very precisely we can determine the spectrum like this. All right, so this is an overview of current Terahertz spectroscopy, and I want to introduce the ATR attenuated total reflection spectroscopy in Terahertz vision. And in the morning, ultraviolet ATR people will explain the technique. So it's the same, almost the same. So we have internal total reflection, and outside the prism we have evanescent wave. And if you put some material here, we can measure the absorption by just seeing the transmitted light. And the important thing is this is quite polarization dependent. And we can prepare TN and TE mode here, just rotating the input polarization, and see what's happening. And many interesting modes we can see using this ATR technique. I want to show you just one example, but before going that, I want to show you the measurement system. So I just show, this one is a transmitted system, like the same. And here is the sample position. And in our special technique is we invented a DAF prism method. Maybe you don't know DAF prism, but the DAF prism is after internal total reflection, original optical path does not change. This means that if you just insert the prism here, original path does not change. So this is quite easy to align and optimize a system. And just using this Teflon or silicone, depending on the material you want to measure, you just insert prism here, and you just place the material on the top of this surface. All right, so one example is a surface mode. And surface mode, every material we have surface mode. In the metallic material, we have surface plasmon, and also in the phonon, dilated material, we have phonons in the bulk, but also we have surface wave of the phonon. But normally, we cannot see the surface optical phonon mode. But using this technique, we can easily see the surface mode. And this is the example of cesium iodide. And in the case of cesium iodide, we have TO phonon mode around 1.9 terahertz. But you put this crystal to our terahertz API prism and measure the transmission. Only in the case of TM mode, we have very large absorption. And nothing happens for the TE mode. So this means that this absorbed mode should be TM mode. And this position is not the same as the TO mode. This is a signature of the surface phonon mode because surface mode appears between around the dielectric constant equals 0. So some textbooks of solid-state material, solid physics, surface plasma also appearing around dielectric constant around 0. So you know, TO mode, and we have LO mode, longitudinal mode. And in between, we have zero crossing, if you consider the dielectric constant. And around the zero crossing point, we have surface mode. So this is really the signature of the surface mode. And using Terahertz technique, we can measure the surface mode like this. And also, we can measure many materials very easily. It's a kind of easygoing spectroscopy method. Just pressing the powder and push to the prism surface, you can measure this optical absorption spectrum like this. This is the case of sucrose. We take a sucrose powder and just put on the surface. So very easy. Without using pellet, we can measure the spectrum like this. And of course, similar happening for the liquids. You place the liquid on the top of the prism surface. You can measure the spectrum of any liquid. And today, I'd like to show you about the only water case, but any alcohol and many liquids you can measure. So details, please look at these papers. I showed these papers on the abstract. And today's our system covers the frequency range from 0.22 to 7 terahertz. All right, so I'd like to go into the water spectrum. So what is important in Terahertz region is that there is picosecond dynamics of water. And because 1 terahertz is 1 picosecond. And if you consider Debye type relaxation, so absorption peak is around 20 gigahertz. So it's corresponding to 50 picosecond. And you know, so hydrogen bonding strengths were existing around several terahertz. So time scale of dynamics should be Terahertz region. So this is the importance of the Terahertz spectroscopy of water. And I will show you later some stretching mode and also vibration mode also existing in this frequency region. It's a collective, hydrogen bonding is important, collective water motion. And also, another important topic is we can directly compare with the molecular dynamics. As you know, molecular dynamics computer can calculate only the fast time scale, not the millisecond, not the microsecond. They only calculate before nanoseconds. This is quite fit to the such a calculation method. Terahertz spectroscopy explains the dynamics in fast time scale and can compare with the molecular dynamics simulations. All right, so this is our typical result. So this red curve is obtained, this one, real part of dielectric constant and imaginary part of dielectric constant. And this one is a microwave experiment. And this one is infrared. And this red one is a telespectroscopy. And normally, we have this one is a Debye conventional Debye relaxation, you can see some deviation from this Debye. Some part existing here, and we have two vibration modes here. So we must consider at least two Debye components and also some vibration mode. And this is a cross-looking around 1 or 2, 3 terahertz, real part and imaginary part. And this one is a temperature dependence. And also using ATR prism, temperature dependence you can easily measure. Just changing the prism temperature itself, you can measure the temperature dependence of the liquid. And you can go into the super liquid phase. This one is a -6 degree. You can measure also a -10 degree. But if you speak loudly, easily you can have ice on the top of the prism. Some small shock induces ice state. But anyway, you can measure below 0 degree if you cool down very carefully. And you can see real part doesn't change so much. And imaginary part changes a lot. And you can extract or remove this conventional Debye component. Maybe you know already very well about the conventional Debye component. So we can see that residual component in the Terahertz region. So this one is a residual component. We subtracted the first conventional Debye. And this is almost flat. This is imaginary part. Maybe you can see previously slide, sorry. Very little change in imaginary part. But if you remove everything in the conventional Debye, almost no change. In this temperature region, it's a little bit strange, but this is quite important issue for this residual component. And we try to fit second Debye component and also 5 terahertz into molecular solution mode. And this is a result. So this one is for second Debye component. This is the strength of the second Debye component. And this is the time constant of the relaxation for terahertz second Debye component. And this red curve is the previous report by Ren. But you can see clear deviation. We understand this deviation coming from, they are not considering the vibrational mode. Their measurement is only limited below 2 terahertz, so they cannot remove accurately the vibrational mode. So our result is more accurate to separate this second Debye. And you can see, so amplitude doesn't change so much. This is temperature. But and also time constant is around 300 femtosecond, and also not so changed. This is the signature of the second Debye. And for the help of the understanding, we look at the high pressure experiment. So this is reported by Dr. Okada in 1999. And this is a high pressure, high temperature experiment of the Dielectric constant. And in this experiment, they obtained. This one is a conventional Debye. So this is a diluted region in the high temperature, superliquid phase. And relaxation time is long. But if you increase the density, so relaxation time is decreasing. But after critical point, they are separating into two. So this is conventional Debye. And this one is some free light water. So if you consider this very simple model, collision model, and consider the density and kinetic energy, average kinetic energy, we can estimate the collision time. And actually, collision time exists around here. So this is the kind of signature of the free light water in bulk state. And our result existing are here. And this is almost the same as this free-like water state. So this means that we obtain second Debye component. And one suggestion is even in an ambient temperature and the pressure, water may have a free-like component. And they appear as a second Debye component like this. And I show you briefly the collective 5 Terahertz mode. And this is an isotope effect. So H2O, B2O, and H2O18. And for the reference, I show you the AIS spectrum. And I obtained easily. I taught already how to make AIS. But after making AIS, so this low frequency absorption disappears. Oh, of course, this is a Debye component. So disappears in the AIS, but appear in these modes. And these modes are attributed to the zone boundary of the phonon mode of the AIS. Because it's a high density of state, it's a zone boundary. And you can see T8, LA, LO. And this 5 Terahertz mode is almost the same region. Because interatomic stretching, intermolecular stretching mode is a kind of zone type motion. So frequency range is the same. And if you consider the amplitude of this vibrational mode, strongest one is H2O, and weaker one is, the weakest one is D2O. So this is also consistent with the X-ray Raman spectroscopy because H2O is more disordered than D2O. And this really corresponding to this X-ray Raman spectroscopy result. And maybe next talk, Dr. Shiraga will show you very broadband spectroscopy and more details about the vibration mode and deviation from the conventional Debye in the next talk. All right, so the final subject should be hydration. And how to determine the hydration effect in Terahertz region. So this is a typical dielectric loss of the water. And this one is a water 20 gigahertz peak. And the second Debye and some stretching mode. Sorry, this one is a typical Debye mode for this dotted curve. And if you add some solute, so in such case, some solute absorption appearing in low frequency region. And also, so water is attached to the solute, so motion also becomes slower. So water absorption moves from here to there. So many people already study this low frequency water relaxation mode already. But using Terahertz spectroscopy, we only see the decrease of free water state. So by looking at this decrease, we can estimate how large molecules remain as free and how many molecules are attached to the solute. We can estimate just seeing this the spectrum of the Terahertz region. So one example is a sucrose. So if you mix the sucrose to the water, and Terahertz spectrum decrease like this. So this is a pure water. And if you add sucrose, so imaginary part decrease like this. So this red curve is a sucrose crystal absorption spectrum. So nothing existing around 1 terahertz, but a decrease occurs. So this decrease is coming from the decrease of free light Debye water. And by counting this decrease, we can determine how large molecule going to hydrated state. And I skipped everything about how to calculate. Please look at this paper. But using this technique, we estimate the number of hydrated water should be around 35. And this number is very close to the result of molecular dynamics. And molecular dynamics result is quite far from NMR and other slow experiment. So this is really, we are just seeing the fast process and a very nice correspondence with the molecular dynamics, like this. I'm using the, how many times I have? Already, sorry. So I just show you the lipid result. Maybe you're interested in lipid. And also, if you consider bilayer lipid, so inside we have many waters. So inside, how many water molecules are locked, well, connected to the lipid, and how many waters are free? This is an important issue. So we did a similar experiment in this lipid, and this is so just we mix the lipid into the water, increase the density of the water. So full hydration occurs around here. So using X-ray diffraction technique, we can determine the space between lipids, bilipids, and full hydration occurs around here. So the increase of the distance and some constant area period. And we determine the hydration number using the Terahertz spectroscopy. This is the result. So if you increase the lipid density, water, so we really see the decrease, very large change we obtain. So by looking at this change, we can estimate the hydration number. So we're using this type of bulk water term, hydration water term, and the lipid term, and also taking account into this local field effect correctly, and measure the number of hydrated water. So only 3 free parameters. We fit such a spectrum, Terahertz spectrum, using only 3 parameters, and we can determine the number or density of hydrated water. And this is a result. So we have, so 25 angstrom is the distance, typical distance of the bilayer lipid. And 10 angstrom from each side is hydrated or slow water. And remaining 5 angstrom should be free-like water. So this is our result, and the correlation length of hydration effect should be 10 angstrom. So using Terahertz array technique, we can determine the hydration number like this. All right, to summarize my talk, so I explained Terahertz ATR technique, and this technique can monitor the water dynamics and also hydration state. And then in the future direction, I suggest wideband spectroscopy, show you limitation of the Debye model, and also time resolve study can see a chemical reaction or dynamical change of the biological molecules, and also hydration dynamics in a living cell is quite an important issue. Thank you very much for your attention.
Time is coming, so let that comes.
Thank you very much for the wonderful, always very wide talk and informative. I have 2 questions. One is, when you have worked a lot with terahertz and optics, what is comparison, what terahertz can do, and compared to infrared, the rest of the regions for the water? And number 2, if you can go to your 26th slide about the Debye integer, imaginary pattern, right? Yeah. 16. Not
So-
here. Oh, okay, 26 here. I'm sorry. You said that nearly, I mean, you don't see anything, but I think water works with the very small numbers. And I think if you blew up this, there will be lots of very useful information. It's just a comment.
Okay, thank you very much. And maybe another interaction like mixing some solute or hydration effect. Maybe many things happening in this region. You're right. And also, what is a good point of the terrace region should be collected motion of the water. And so hydrogen bonding network is, if you look at the femtosecond time scale, it's quite solid. But if you look at the slow time scale, it's fragile. So if we want to understand the network itself, this terrace region is important. And also, big molecule has the eigenfrequency around terahertz. So this is quite much to this hydrogen bonding frequency. And if you consider why this biological molecule has this form, maybe it should be relating to these dynamics. So when we understand the hydrogen bonding network itself, terrace region is important. This is just a comment.
Thank you very much. So time is coming. I'm sorry. So let's go to the next topic.
Thank you very
Thank you
much.
very much.